What's up everyone? I recently released an update for this plugin that I once made, Overdrive ReNEO, a tribute to the iconic MDA Overdrive plugin from the golden era of VST plugins. In this update I added a gate parameter and it sounds like this. It's just a pre-distortion gate and it makes sure that there is a little bit of silence between the breaks to increase the impact of the distortion, because otherwise it would just be one big mess of crunchiness. And this video is going to be actually a coding tutorial again. I haven't made one of these in a while, and it's going to be about dynamics processing. Here's the table of contents. First of all, I will implement the simplest gate imaginable and also show you why it sucks. Then I will show you how to make a good dynamics processor. And if you haven't fallen asleep at that point already, we will look into some deeper math of transfer curves. Let's get started. Here we are in a simple producer-based project where I just prepared a bunch of parameters to start with. Threshold, ratio, knee, attack, release and makeup gain. So far none of them are implemented, but we will start with makeup gain right now. This is the header where I will write all of the code. So now this is what all of my DSP classes always start with, and I will now add the parameters to this. Now to make it a little bit more clear what units I'm going to use, I will also write them to the parameter names. Threshold, ratio and knee will be in decibels, makeup as well. Attack will be in milliseconds and release as well. So now to start with, we need a little function that can help us converting a decibel value to gain. Perfect. Gain to decibel is useful as well. Makeup gain done. Perfect. Next up I want to make sure that there is an individual dynamics processor for the left and the right channel. Dynamics processor mono. So this one will obviously not get num channels and only get a few samples. Makeup will also not be used. And now the dynamics processor will have an array of 2 dynamics processor monos. And just in case that I will use the prepare method for something. Now I have 2 DINs and I will just loop through the channels and process them. Now that I don't have to care about the channels anymore, I can focus more on making a really naive gate. GitHub Copilot already tries to suggest some stuff to me that I should do. It looks a little bit messy and I won't do that, but thanks I guess. So what could be the most naive thing that you could do in order to write a gate? I think it could work a little bit like this. You just say, yeah, this is my threshold, and everything that is below it becomes 0 and everything else stays where it is. Let's implement that. So we got the dry sample out of the array of samples. Now we want to rectify it so that we only get positive values. Now if the rectified signal is below threshold, then we say samples should be 0, and else nothing should happen. Yep, that's a gate. Let's test it. I mean, it does sound kinda like a gate, but it also sounds pretty crunchy. Can you already guess what's going on? Let's look at it in an oscilloscope. Okay, so here we have an oscilloscope and we can inspect what's going on. Basically, it turns the sound on and off all the time. Like we have a lot of these places where it just can't decide if it should play something or nothing in really short intervals. Then for a while it just stays on when the waveform is high enough, gets crushed again for a while, and then it plays the other half of the waveform. So yeah, it can't even play a single waveform without crushing something, and that's why it sounds so crushy. And that makes a lot of sense, of course, because a real wave is not like this. A real wave is more like this. So our little gate would be hit like all of the time. Something is a little bit close to zero, it would hit non-stop, and that's what it does. Yeah, so now we need a solution, and I propose that we have to separate different jobs with each other. In order to make a signal smooth, it's not enough to just rectify the signal, which would just turn everything around. We already did that, but what you have to do on top of that is applying an envelope follower. This envelope follower would likely have a very high attack setting so that it directly jumps up, but when it falls we would have a long release time so that it never really reaches zero, and only when there was no wave for a long time can finally reach zero, and then it would hit the gate righteously. That's what we want to do. However, how do we even combine this envelope follower approach with different kinds of dynamics processing? Like, you have probably seen this concept of a transfer function, and if you haven't, then I will just load Kilohertz dynamics now, because I think they managed it very well to like visualize what's going on. When you turn this down, you got a downwards compressor, and when you turn it up, you get an upwards expander. Oh, it doesn't let me turn it up actually, but it would be an upwards expander if it would let me do that. And if you turn the lower thing down, you get a downwards expander. And you can already hear that this is pretty much a gate as well, so we are going for that first in this video. If you go up with this, you get an upwards compressor. And you can hear that this is the typical sound that you get from OTT kind of plugins as well. So this is also really exciting. But how do you even combine this whole transfer function thing with the concept of an envelope follower? This is a question that I'm going to answer in this video. Alright, so now I'm going to show you how it should really be done. And in order to do that, you go to the Dynamics Processor Mono and throw out of the window what has already been done. Start from scratch. And with from scratch, I mean something that I just prepared for you, which is a level detector, and I will explain how it works very soon. But first of all, I will just add it here. Level detector. Now the level detector is finally something that needs to be prepared actually, because sometimes it uses the sample rate and it has a buffer, which is a float vector. We also have a low pass filter in here and some values called attack X, release X and envelope. You will see what they are good for. So for each block, the level detector is called with a buffer of samples, with the attack in milliseconds, the release in milliseconds, and with num samples. We get the X value from attack milliseconds and release milliseconds, which is just a little optimization that I implemented for my specific low pass filter. All you need to know is you kind of need to have the ability to quickly change the coefficients of your low pass filter, because now you start to synthesize over your buffer, and for each sample index you rectify the signal, convert it to decibels, and then you do the thing. If the envelope currently is below the rectified input, then it's attack state, and else it is release state, and then you just start low pass filtering into the envelope variable and you return the envelope variable. Let's implement that. Cool, now we already got the level detector settled, but now you might be wondering, how do we get the transfer curve also into this equation? So let's loop over the samples. And for each sample, we get the dry sample out of it, and we get the sample from the level detector. Perfect. Now the idea is that we will have some function that returns a decibel value, and it will look a little bit like this. It doesn't exist yet though. And the wet signal will just be defined as the dry signal times gain downwards expander decibel converted back from decibels to gain. And you can just put that into your samples buffer. This is the plan. But how do we actually get here? In order to figure out an easy transfer function, you can just go to Desmos and just say something like, okay, I got a threshold, maybe it can go between -10 and 10, I wouldn't go too far for decimals because this is more for visualization purposes. And with a ratio that starts with 1 and it can go up to like whatever 4. I like to use stepped values here, just looks a little bit nicer. And then you can start tweaking. And we know that we want to have some sort of output, so I call it y. And y is going to be if x is below threshold. Then something called y ratio will happen, and else it will just be x. Because x represents that nothing changes. It is a linear function. Now I have to add yr as a slider. And as you can see now, when I'm turning the threshold, we get the value just 1 for whatever is below threshold, which obviously is wrong, but good enough for now. And everything above threshold just acts as a linear function, which is exactly what we would expect. And as you can see, we need to go to the lower left quadrant because we are in decibel space here. So we are working with values that are below 0 all the time. That's something to keep in mind. Now we want to incorporate the ratio. So first of all, let's replace this with x and also draw this curve. Just see what happens if I multiply this with r. And as you can see now, with increased r values, we get it to be steeper, and that's already exactly what we need for a downwards expander or a gate. Now we just need to figure out how to like put it somewhere else. So let's just try -t. Yeah, that was the right direction. +t, that was also the right direction, I think. So now we have like shifted it to the left and down by a threshold, which makes a lot of sense because this is a linear function, so we can just move it with the same value. Now this is the origin of this function, and from here on the slope will be applied. Now if I turn off the visualization for this curve, we can only see the resulting transfer function, and we see this is a downwards expander function that we can use right now. By the way, we'll get to the knee later. It's a little bit more complicated, so I will just put that to the side for now. GitHub Copilot says this is correct. If x is below threshold, then x. No, that's already wrong. If x is above threshold, then it is x. And else we have to ratio times, oh yeah, that's correct, I think. So now we got the downwards expander, but that's not all that we need. We also need this function, which computes the gain in decibels from the transfer function by just subtracting the transfer function from the input level. And that way we can also do this, just write a function that directly computes the gain decibels from the downwards expander. So let's just take this function and use it here. Shall we try if it works? Something about this didn't work. Alright, got it. So here in the level detector, I set a breakpoint. I wanted to check out if the filter is doing the right thing. So I'm looking at the buffer and I can see that there is a -infinity in there. And I probably know why that is, because you know, you are using the gain to decibels function here. The problem with decibel values is that decibel values have no concept of silence. That's why in projects like this, you always have to have a minimum decibel value defined somewhere. So here I will now say if rect is 0, then this is going to be min decibel, and only if it's not, I will use this function, and this will likely fix it. Yeah, that looks good. Yeah, that sounds pretty much like a little expander right now. Already better than a gate. We have threshold, we have ratio, we have attack, release, and we have makeup gain. The only thing missing right now is knee. So here we are back in Desmos, but this time with a sexy little graph that is finished and has knee. At the moment, knee is turned down to 0, which means there is no knee. And as you can see, this is reflected in the graph. It is just a normal downwards expander with ratio. And it has 2 points, but both points are at the exact same place. But once you turn up knee, it moves away from the center of where the threshold was to the right and to the left and just opens up. And as you can see, then you get the possibility for some softer transition between the dynamics processed signal and the dry signal. That's exactly what knee is for. You have already seen a little bit of an Easter egg here. I wanted to keep it for later, but now you've already seen it, which is that you can put ratio to negative values and actually have something else then, like when you have the positive values, then this is definitely a downwards expander. Then you go to the values below 1 and you get something more like an upwards compressor for some reason. So if you ever decide to make a plugin that has an upwards compressor and a downwards expander in the same parameter, you can easily do that. And if you go below 0, then you can even let it go really upwards. And I'm not even sure if I want to hear what that sounds like. That must be terrible, but it works. It is possible. You can do it. And that's pretty cool. Okay, so now I will explain what's going on. You have already seen this is threshold, this is ratio, and this is knee. And K2 is just defined as half of K. This way of creating a transfer curve, while not being the only way to make one, is one where you go to the right and to the left of the threshold point by half of knee. So you need this value sometimes. And I already prepared T0 and T1 as half of knee down and half of knee up from threshold here. So these are also threshold values, or more like threshold offsets. Now we have two functions here. One of them looks like this when I turn it on and off. The other one looks like this. And then there is also the linear function here. That's just a normal linear function. And of course, y, which combines all of the functions with each other. If x is smaller than p1, the lower point here, p1's x, then we take the output for the ratio thing. Else, if it's a little bit bigger, so if it's just below p2, then we take the knee output. And then, if none of that was the case, then we just use x. This is what this term says. It looks a little bit complicated, but actually I think it's quite nice. It took me a long time and a lot of help to figure it out, but still, I would say it's easy to understand once you get it. And you get it now by looking at this video. So the first thing you have to do is making a quadratic equation with an offset of the point that has the normal linear function on it. Sometimes that is the first point, sometimes that is the second point. You know, if you have a downwards compressor, then this is going to be the lower point. Then you have a value that I just called M because it squashes or opens it up depending on your ratio and knee values. And up here in the output of the knee, we just say, okay, we want the normal linear function plus the squishy M thing times the quadratic equation that has been shifted. You might be wondering what happens if you not use M. This would happen. You would get a curve that already goes through P2, but it just doesn't have the right size yet. That's why there is this M. And there is a pattern in how you have to design this M value in the different kinds of transfer functions. The pattern is that it always has something to do with 1 divided by 2k. Only the thing that is up here is different every time. But I will show you some other examples now that will show you that it's always the same pattern but just slightly different. So here we have the code for the upwards expander, and there you can see that this M was r-1 divided by 2k. Then here we have the downwards compressor function, also something with 1 divided by 2k, but this time it is 1 divided by r-1. And here we have the upwards compressor 1 divided by r. I will copy the links to these Decibels tables into the code if you want to watch them. Now let's implement the downwards expander fully with knee. In order to do that, we just have to add our little knee parameter here. So if we are below the lower threshold value, then we just take the normal ratio. Easy. Could even start optimizing this a little bit at this point, since we only really need T1 if we get behind this first if. But talking about optimization, I'm very well aware that a lot of the stuff that I'm currently writing is not very well optimized, but this tutorial is just meant as a starting point for everyone. You can find your favorite optimizations yourself. Now there is one thing that I will do a little bit differently than in the Decibels though, because I noticed one thing: when knee is turned down to 0, then M is undefined, because 1 divided by 0 is well, undefined. I don't want my code to break because of something like that, and I think the best way to do that is to just not ask for the knee case as the second case, but as the last case. If x is bigger than t1, yeah, then we return x, because if it didn't return from these two things, then we know that there actually is a knee state right now available for us. Okay, I think this should be it. Let's test it. Yeah, we can hear that on these extremely aggressive settings with attack and release turned down to unreasonably small amounts. When you turn down the knee, it just sounds super crunchy, and when you turn it up, it's still crunchy, but it's, you know, the thing that knee does, where it is just a little bit polite. Yeah, with more reasonable settings in general, it just becomes pure bliss. Sometimes it chokes the transient a little bit, but you know, we didn't implement any look ahead, and I would say that this is definitely a topic for a different video if anyone is interested, but for now we will call it a day. And yeah, happy coding. Make a lot of compressors with a lot of different compression types. I'm looking forward to all of your little creations.